안녕하세요. 저는 서울과학기술대학교 데이터사이언스학과 석사과정 재학생 하산풀이라고 합니다. 저는 Detecting DeFi Fraud with Graph-TransformerLanguage Model이라는 논문을 발표하겠습니다. 이 논문은 지난달에 IEEE Transactions on Information Forensics and Security에 저널에 발표됐습니다. 발표를 연가로 진행하겠습니다. I will follow this outline for today's presentation. Starting with the introduction, let me briefly outline the problem that this paper addresses. DeFi applications, which are decentralized finance apps in blockchain, faces serious security threats, including smart contract vulnerabilities like re-entrancy attacks, phishing scams, and money laundering. This results in significant financial losses. The key challenge is that blockchain transaction data is inherently complex and multimodal. To detect fraud effectively, we need to capture both the structural patterns, how the accounts are connected in the transaction graph, and the temporal patterns, when and in what sequence transactions occur. Existing methods struggle with this because they focus on either graph structure or sequential patterns, but not both together. This creates a critical need for better real-time detection of suspicious transactions and malicious accounts. This paper proposes TrxGNNBERT를 to address this gap by combining GNN and Transformer in a unified architecture. Let's discuss the limitations of existing methods. There are mainly two types of approaches. One is a GNN-based approach, which, for example, GCN, Graph Attention Transformers, and GraphSearch, which learn transaction graph structure effectively. However, it has limited ability to handle textual or semantic data, for example, call traces. And the another approach is transformer-based methods like ZipZap, BERT for Ethereum, which excel at processing textual sequences. On the other hand, it ignores graph structure and dynamic properties, as well as address leakage problem during the pre-training. There are four fundamental challenges that this paper tried to tackle them. The first fundamental challenge is data complexity. Transaction data is multimodal, consists of numerical, textual, and categorical with both sequential and graph structure. The second challenge is representation misalignment. GNN and transformer embeddings reside in totally different and incompatible feature spaces. And the third one is information flow bottleneck. And the fourth challenges is structural and sequence trade-off. Existing methods sacrifice one for the another. Once again, just quickly recap the problem, gap knowledge, and the contribution. As we told before, the DeFi fraud detection challenges are that it requires capturing both sequential patterns using graph topology as well as the temporal patterns, like the transaction sequences. The current approach limitation is that it uses one of the GNN-based methods or transformer-based methods, which fail in one of the capturing graph topology or transaction temporal patterns. So this paper proposed the TrxGNNBERT architecture, which uses early version of GNN enhanced embedding into transformer encoder. Moving to the methodology this paper proposed, it follows a bottom-up pipeline, which first constructs a transaction subgraph around a target transaction or target account, and then expand it. And the second step is tokenize nodes and edge attributes using a BPE tokenizer, and then generate embeddings. After the embeddings are generated, it will inject a GNN module, and then it will project a linear projections to feed it into transformer encoder in a chronological order to preserve the transaction orders. And lastly, it's sampled to. And lastly, in the sampling step, it aggregates nodes embedding into a single vector, and it will use downstream tasks, for example, suspicious transactions or account detections as a classifier. There are two types of accounts in Ethereum. One is externally owned accounts, and the second one is smart contract accounts. Now let's deep dive into the learning process of this proposed method. This diagram shows the complete learning pipeline, starting with a transaction subgraph, the tokenized nodes and edges attributes in step 1, then embed them in step 2. Step 3 is crucial because it injects GNN enrich embedding with the graph structure. Step 4 fits this into a transformer encoder in chronological order for temporal patterns. On the left side, you see pre-training. They mask random tokens and train the model to predict them, learning deep representations. On the right side, it is the downstream task which pull the final embeddings and classify transactions. The same architecture handles both phases, with early fusion ensuring graph structure and temporal information interact from the start. Now let's see the first step, which is transaction graph, subgraph construction. The algorithm for the subgraph construction is first initializing the starting node, which could be around the target transaction or target account. The second step is collect all transactions from n nearest block. The n here is set to 200. And then the third step, it expands iteratively for k hops. And lastly, it sorts transactions chronologically to preserve temporal order. And there are two types of strategies used. One is transaction-centric for transaction classification, which initialize with target transaction account and expand it over n blocks. And another one is account-centric, which is used for account classification, and again, it initializes with all transactions of the target account and expand it over n blocks. The next step is tokenizations. Using BP tokenizer, which trained on Ethereum data, it will tokenize both the node attributes as well as the edge attributes. The node attributes are shown in the table 1, which are the attributes is contract, whether it's a contract or externally on the account, or the account balance, account random number, contract code. And the edge attributes are transformer account, transfer amount, gas units, gas price, and the other account related and transaction related properties. Then they convert the tokenized layer into dense vector in the embedding layer, and then they will inject a graph isomorphism network GON. The input here is X nodes and X edges. The output will be structure enhanced embeddings. And the reason why they are using GON is because it handles both node and edge attributes, and it's preserve a strong structural learning of the embedding. Step 4 and 5 are straightforward. We project dimensions to match the transformers, then feed embedding into chronological order to capture temporal patterns, then use sampling to get a single graph representation for classification. For pre-training, they use masked language modeling on graphs. They randomly mask either node attributes like balances and fees, or edge attributes like transaction amounts. The model learned to predict these masked values, capturing semantic and structural patterns without needing labels, using these loss functions for both node attribute masking as well as the edge attribute masking. And the pre-training dataset was 60,000 Ethereum transactions during August to September of 2023. Now let me highlight what makes this method different from existing approaches. First, early fusion versus late fusion. Unlike previous methods that combine features at the final layers, the author of this paper inject structure-aware features at the embedding layer. This means graph and sequential information propagate through all transformer layers together, which enable deeper interaction. Second, unified feature space. The GNN and transformer operate in the same feature space from the beginning. This eliminates the representation misalignments problems where graph embeddings and sequential embeddings live in incompatible spaces. And third, no address leakage. This is important. Unlike BERT for Ethereum and ZipZap, which use actual addresses during the pre-training, this paper doesn't. This gives better generalization to new unseen addresses that weren't used during the training data. And finally, temporal structure balance. The GNN captures how nodes are connected, while the transformer captures when and in what sequence transactions occur. Neither modality dominates. They work together. This balance is essential for detecting sophisticated fraud patterns that span both network structure and time. With that being said, let's now move to the experiments. First, the setup and results. The dataset which used in this experiments are three types of datasets. One is transaction large, transaction small, and the address DAC. Transaction large was were about 4,320 transactions in three classes: normal, phishing, scam, and transaction small. 598 transactions in two classes, normal, phishing, and the address DAC were about 11,581 accounts in two classes, normal and suspicious. It was compared against 10 baseline methods across three categories. Graph embedding, which includes deep walk, transaction to wake, roll to wake, and GNNs like GCN, GOT, GraphSec, and transformers like CodeBERT, GraphCodeBERT, ZipZap, BERT for Ethereum. In table 3, we can see a comparison of different approaches across those three categories. Here we can see that this proposed method include all of the properties, for example, EOA, externally owned account, as well as transactions, and age info. Comparing the performance with the other baseline models, we can see the proposed model outperform almost all the models in all three datasets, as you can see here in the F1 score as well as the accuracy. It outperforms all the existing methods in three different categories like transformers, GCN. The others of the paper used the ablation studies for the experiments, which strategically removed some of the components from this architecture and see how it affects the performance. Let me discuss what this ablation studies reveal and what matters in this proposed model. First, pre-training has a positive impact, adding 2.2 accuracy and 1.4% of F1 score. While not massive, it's consistent improvement without any labels. Second, among different GNN architectures, GNN outperforms others by 4.5% over the second best GAT BERT. This is because GNN can handle both node and edge attributes effectively. Third, and most critical one is the subgraph structure is absolutely essential. When they remove it, accuracy drops by almost 30%, which shows that local graph context is the most important component in this system architecture. Fourth is node attributes are more important than edge attributes. Removing node causes severe performance degradations, while removing edge causes moderate decline. Fifth, temporal ordering matters. When we randomly shuffle the node sequence, performance drops, confirming that the chronological order helps the model to learn execution path. Finally, early fusion outperforms late fusion by 3.3% in F1 score. This validates the author design choice of injecting graph information at the embedding level rather than combining feature at the end. Now let's discuss the strengths and limitations of this proposed approach. The strengths are clear. The TrxGNNBERT achieves the best performance across all the three datasets, effectively fuses structure and semantics. However, there are some limitations. First, there is computational asymmetry between GNN and Transformer. The GNN can have unpredictable memory usage, which with dense graphs. Second, they limit subgraph to 200 distant transactions, which might miss long-range attack patterns. And third, there is a dimensional paradox. Higher dimensions doesn't always improve performance, suggesting optimization challenges. Some additional observations are like runtime is about 20 seconds per transactions, but this is mainly due to the API query bottlenecks, not inference. They only tested on phishing and scams, not flash loans or other type of DeFi frauds. And the data collection was quite expensive. It costed almost 1,200 USD, and more importantly, they only evaluated on Ethereum during 2023. So generalization to choose blockchain on time period remains to be validated. TrxGNNBERT achieve state-of-the-art performance on DeFi fraud detection by addressing a fundamental challenge, combining graph structure and sequential patterns in a unified architecture. The key to success is early fusion of GNN and Transformer. By injecting structural information at the embedding level, both modalities interact deeply throughout the model, not just at the final layer. This paper comprehensive evaluation against 10 baseline confirmed that superiority across multiple tasks. The evaluation study validated that each components matters, particularly the subgraph structure and node attributes are critical. And pre-training with masked language model significantly boosts the downstream task performance. Looking ahead, there are exciting directions. First, extend to other security threats like flash loans and cross-chain exploits or other type of DeFi fraud detection. Second, optimizing for real-time deployment. The current 20-second latency needs improvement for production use. Third, improving subgraph extraction to capture more complex attack patterns. And finally, validating generalization across multiple blockchain beyond Ethereum, for example, other blockchain network like Solana. The architecture itself is generalizable, but practical deployment at scale require further optimizations. That's all. Thank you for your attention.